In this section, we're going to talk a lot about titrations. And in the lab, titration is a really helpful analytical technique. If you've taken previous chemistry classes with me before, in Chem 221, we looked at the determination of an unknown chloride lab, where we were able to use a titration to find the percent chloride in an unknown. In an acid-base titration, usually the goal is to find, say, for example, the molarity of a solution, or you can also find the molar mass of a solution. Lots of different things that we'll be exploring. But in a nutshell, in a titration, you have a burette, which is this kind of thing here in the top right there. It has what they call the titrant. And in the beaker or Erlenmeyer flask or whatever you're using, you have another solution called the titrate. So the titrant from the burette is being added to the titrate. And there's different regions in a titration, and the regions, honestly, are just mole-based. When the titrant and the titrate moles are equal, that's when you reach the equivalence point. And that's an important part in a titration, because at the equivalence point, the moles of what you're adding equal the moles of what you started with. Now, in the acid-base world, that would be moles of acid equaling moles of base. And if you know where the equivalence point is, there's a lot of things you can do. A pH meter or a pH probe can be used to analyze the pH at these different amounts. And if you understand what's happening in a titration, the pH meter can be really, really helpful. Sometimes people use an indicator, and if you look in the bottom middle part right there, this is a pink to yellow transition. An indicator, if chosen correctly, can be really helpful. It's a visual cue to tell you when you've gotten to this equivalence point. And from the equivalence point, there's lots of information you can find. If you don't know what kind of acid you have, or you don't know the concentration, or the base for that matter, you can do it. Most of the time, how it works is you start with either a strong acid or a strong base in the burette of known concentration, and then you're titrating it into an unknown acid or unknown base, the opposite, in the beaker. But there's lots of different variations, and we're going to explore them all as we go through this section. And by the way, titrations can be more than just acid-base. They can also be precipitation titrations. You can have a redox titration. There's lots of different kinds of titrations. But in this section, we're, of course, going to focus on just acid and base titrations. These three little animations show three possibilities when you're adding sodium hydroxide from the burette to an acetic acid solution. And you can see in the first one in the upper left, at first there's a little bit of a curve, but then it goes pretty mellow. Like you don't see a lot of it. It's very, the rise is very gradual, okay? And this part is important. This is actually going to be a type of a buffer region. We'll talk about this in a little bit. However, once you get through this region, then in the second graph, you can see that, man, that titration curve really spikes up really hard. And that spiky point where it's really steep right there, that's really where the equivalence point is, the equivalence point between the acid and the base. And then finally, because we're adding sodium hydroxide to an acid, after a while, when you get past the equivalence point, then you can see you have this really sharp kind of curve part right here. That means then that the acid that you started with has been exhausted, and now the base, sodium hydroxide, dominates. Now notice this is kind of like an S, all right, if you look at the far right one. Sometimes they call these titrations S curves. It's really only an S if you have an acid that you start with and you add a base to it. We'll see that you can have reverse S curves, but if I talk about an S curve or you hear an S curve, that's what it refers to. Also, knowing the chemicals that you start with helps you predict the form of the graph. So we started with an acid, and you can see that the starting point was acidic. It had a pH less than 7. And at the end, because only the strong base was there, you can see that the pH ended much greater than 7. So knowing these kind of things can be really helpful when it comes to an acid-base titration. And that's what we'll be exploring in this region. This is what they call an alpha plot. It shows how the moles change over time, all right? And this is moles of the acetic acid on top. And you can imagine that if you're adding sodium hydroxide, the moles of the weak acid will absolutely diminish. However, if you remember from the last section, as a weak acid is used up, the conjugate base begins to kick in. So the conjugate base of acetic acid is the acetate ion, and it is basic. Notice as the acetic acid amount decreases, the acetate part starts to increase. So the acetate ion is a player. And remember, it's a base that kind of complements or goes against, whatever you want to think, the weak acid here. This is going to be an interesting thing. You can have a weak acid and its conjugate base in the same solution at the same time. And that's also something really interesting. Like when I think of acids and bases, even to this day, I think, oh, acids and bases, man, they react, a lot of energy. And you wouldn't dare put sodium hydroxide and hydrochloric acid in the same beaker. They would react and annihilate each other and stuff like that. It would be really bad news. But when it comes to the weak systems, you absolutely can have weak acids and their conjugate bases coexisting at the same time. These conjugate pairs are really important, and it leads to the ideas of buffers, because if you have both a weak acid and a weak base, then if you add, say, sodium hydroxide, it'll wipe out the weak acid, but the weak base will still be there. The common ion effect is a tool we'll use to understand what the buffer is all about. So in this section, just to kind of summarize last couple slides, we're looking at acids and bases together. And we're going to see there's a difference between when strong acids and strong bases are together versus, say, strong bases and weak acids, which is what we're talking about, or strong acids and weak bases. These conjugate pairs, the weak acid and their conjugate base, or the weak base and its conjugate acid, have some really unique pH effect. And it results in what's called a buffer. A buffer is a special form when you can have both acids and bases together. They must be weak and they must be conjugates, but it is something that's really interesting. So again, just hang back. Let's check out this material and see what we all have to do here.